Welcome to our exploration of quantum computing for dummies. Welcome to the world of quantum computing. Unlike classical computers that use bits to process information as zeros and ones, quantum computers use quantum bits or qubits. These qubits can exist in multiple states at once, thanks to the principles of quantum mechanics. In this video, we'll explore the fascinating concepts that make quantum computing so powerful and different. Qubits are the building blocks of quantum computers. While classical bits are like tiny light switches that can be either on, 1, or off, 0, qubits can be both on and off simultaneously. This is called superposition. Imagine spinning a coin. While it's in the air, it's both heads and tails until it lands. This ability allows quantum computers to process a vast amount of information at once.
Superposition is what gives quantum computers their incredible processing power. When qubits are in a superposition, they can represent multiple possibilities at the same time. This feature enables quantum computers to solve complex problems much faster than classical computers. Picture a library with millions of books. A classical computer reads one book at a time, while a quantum computer reads them all simultaneously. Another mind-boggling aspect of quantum computing is entanglement. When qubits become entangled, the state of one qubit instantly influences the state of another, no matter how far apart they are. This connection, which Albert Einstein famously called spooky action at a distance, allows quantum computers to perform complex calculations with unprecedented speed and efficiency.
Just like classical computers use logic gates to perform operations, quantum computers use quantum gates. These gates manipulate qubits through various quantum operations, forming quantum circuits. By applying a sequence of these gates, quantum computers can execute algorithms that solve complex problems like factoring large numbers or simulating molecules for drug discovery.
Quantum algorithms are specially designed to take advantage of quantum computers' unique capabilities. One famous example is Shor's algorithm, which can factor large numbers exponentially faster than the best classical algorithms. Another is Grover's algorithm, which speeds up the search process in unsorted databases. These algorithms demonstrate the potential of quantum computing to revolutionize fields like cryptography and optimization.
Despite its potential, quantum computing faces several challenges. One major hurdle is maintaining qubit stability, known as coherence, since qubits are extremely sensitive to their environment. Errors can occur due to interference from heat, light, or electromagnetic fields. Researchers are exploring error correction techniques and developing more robust qubits to overcome these obstacles. Quantum computing holds promise for a variety of real-world applications. It could revolutionize drug discovery by simulating molecular interactions at an unprecedented scale, leading to faster development of new medicines. In finance, quantum algorithms could optimize complex portfolios. In logistics, they could streamline supply chains. The possibilities are vast and exciting. As technology advances, quantum computing is moving from theory to practice. Companies, universities, and governments worldwide are investing in quantum research and development. Although we are still in the early stages, breakthroughs continue to accelerate progress. The future holds the potential for quantum computers to tackle problems beyond the reach of today's supercomputers.
In conclusion, quantum computing is a groundbreaking technology that leverages the principles of quantum mechanics to process information in ways classical computers cannot. With qubits, superposition, entanglement, and quantum algorithms, it offers a glimpse into a future where previously unsolvable problems become achievable. As we continue to unlock its potential, quantum computing promises to transform industries and redefine what's possible in computing.